should definitely check out his Arsenal project on Kickstarter. He mentioned it in passing, but it's pretty huge. It's like $1 million, way overfunded. It's this cool camera adapt thing that like does machine learning to take good pictures on your camera. But anyways, I'm going to talk about spreadsheets. I'm kind of like nerding out on spreadsheets right now. It may sound a little dry, but my name is Lance Fisher. I work for a company called Submittable. We're based out of Missoula, and we had a requirement a few months ago to get to add spreadsheets into our web software. And this isn't exactly how we did it. It's a way that we thought about doing it, but it's basically kind of like a thought experiment that I ended up taking a little too far. So I thought I'd do a talk on it, and I think it's going to be pretty fun. So I'm sure everybody in here has worked with spreadsheets before, like Excel. Most of the time you're just like making a list in here, but if you're an Excel power user, you can do some really amazing things where you can enter formulas in cells to do math calculations. You can reference other cells to get these calculations to update as you input new info. And I don't know if you've ever thought about it, but what would it take to build one of these from scratch? It's kind of like one of these things that we take for granted, but there's a lot going on under the hood. A little bit of history with the spreadsheets is VisiCalc was one of the early spreadsheets. It was built by Dan Bricklin. He was a student at Harvard Business School back in 1979, and he was working through these spreadsheets in class, on paper, right? And he's like, oh man, I could build a program that would make it so much easier to update these. And it turned into the killer app for the Apple computer. It's one of Apple kind of owes a lot of their early success to the VisiCalc. A couple years later, they ported it to PC, and a couple years after that, Lotus 1-2-3 came out and basically killed the VisiCalc market. Shortly after that, Microsoft built Excel, and the first platform they built Excel for was the Apple. They built it for Mac first. And then a couple years later, they ported Excel to PC, and Excel has dominated the market, and now we're seeing more stuff like Google Sheets, that add this additional sharing capacity to spreadsheets. So that's a little bit of history. What we're going to build today is not the visual part of it. We're not going to see the spreadsheet. We're going to see the code for it. So the interesting part to me is kind of this calculation engine. How do you get these cells to be aware of the other cells? How do you get these cells to know what the formulas are inside of them? So our goal for today is to get this code to work. This code is written in ES 2015, and we'll just walk through what's going on here real quick. This is a test, so we're going to write out this test first. At the end of the day, this test should pass. We're going to create a new sheet, and then we're going to get some cells in there. So we're going to be called sheet.getCellA1, and we're going to set its text to the number 1, a literal. Cell A2, we're going to set it to A1 plus 2. So this references the first cell and adds 2 to it. And then for A3, we're going to set it to another formula, A2 plus 3 times 4. So we'll need to respect the order of operations for this to work correctly. You should do the multiplication before you do the adding. And we should also be able to reference the cells in the correct order. So we calculate A2 before we can calculate A3, because there's a dependency there. We call this calculate method on our sheet, and then we grab the A3 cell out of it, and then we're going to expect that the value of that to be 15. If we can build this, we're going to call it success for today. So there's going to be a lot of code. We're going to run through a lot of code. We're also going to have some high-level ideas. So it's going to go fairly quickly. So if there's little pieces that you kind of miss in the code, don't worry about it too much. All the code for this is available afterwards. I published an NPM package called Cellular.js that you can pull it down, play with it. You can even play with it online right now. Okay, so we're going to move kind of quickly. We see our test is failing right now. The issue with our test here is that the sheet is not a constructor, so it doesn't exist. So first thing we're going to do is we're going to build a sheet. This is how we can define a class in ES 2015. A little bit of syntactic sugar, maybe if you haven't worked with the latest JavaScript, this is the way you can create classes. So we have this sheet class. We're not getting that error anymore, but we are seeing an error about getCell, because we don't have a getCell method in our sheet. So we're going to go ahead and add this getCell. It's going to take an ID, and it should return a cell, but we'll figure that out later. We're just kind of like moving through getting our test to pass at this point. All right, so let's see. We look back at our test. We see that now we can't get the property text. So if you see sheet.getCell and then .text, this getCell, it should actually return something. It should return like a cell object. And this cell object should have a test property on it. So we'll go ahead and implement that. We've got this sheet, and up above it, now we defined another class called a cell. And we're just setting up 3 properties on it. Each cell is going to have an ID, it's going to have text, and it's going to have a value. So the value is like what happens after you calculate it, and the text is going to be like what you enter into this cell. And then for now, we're just going to return a new cell every time. We're just going to new one up and return it, just so we have like an object to work with in our tests, right? And then we'll just refactor that quickly into its own file. So we can just import the cell from the cell.js file and use it inside of our sheet here. And if you look over at our test here, you'll see that the sheet.calculate is not a function. So we're getting a little bit farther here. Down below all those getCell calls, we have sheet.calculate. This is going to be kind of the heart of the thing that we're implementing. But for now, we'll just add a calculate method, and we'll put a little to-do note in there that we're going to want to process the sheet at this point. And our test gets a little bit farther. It's looking for 15. You remember after this calculate is called, it's checking that the value of a cell, the A3 cell, should be 15, but we're actually getting null back from that. So to kind of like set up our sheet a little bit more, we're going to do more than just return a new cell every time. Our sheet's going to keep track of all these cells. We're just going to put them in a map. So a map is like mapping a string identifier of a cell to the actual object of the cell. So inside of our getCell method, instead of just returning a new cell every time, what we're going to do is we're going to get rid of that, and we're going to add this little call that checks our map. It checks our cells that we've been holding on to in our sheet here. And if we have a cell already, we're going to return that one. So this way we can keep track of the state of all these cells, right? If it didn't find one in our map, then it's going to go ahead and new up a cell. It's going to create a new cell for us. And then we'll add it to the map, so we keep track of the cell, and then we'll return that cell out of it. So now we have at this point a sheet that can track the state. So you update all these cells, you add text into one, you go get it, you're going to get that same cell back. You're not going to get a new cell every time. Our test is still failing with this issue. So that last line in our test, the expect cell value to be 15. That's not going to work until we get this calculate method. So I think this is like where the hard part is, right? So I promised algorithms with this talk. The first algorithm we're going to use is the Feynman algorithm. This was introduced by one of Richard Feynman's colleagues, kind of facetiously during an interview. Richard Feynman is like this brilliant physicist, worked on the Manhattan Project, and he also had a knack for explaining difficult science and physics concepts. And he could just solve problems really well because he knew the physics and he knew the math like inside and out, and he could just imagine it. So his colleague suggested we write down the problem. So that's kind of what we did here. We wrote down our problem in the form of a unit test. And then you think really hard, and then you write down the answer. So this is how Richard Feynman solves problems. May not work exactly for us, but there's a really cool Feynman quote that I wrote down here. And he actually wrote this on his chalkboard, and it was there at the time of his death. But he wrote, "What I cannot create, I do not understand. What I can't create, I don't understand." So he wasn't talking about like creating particles and stuff, but more like deriving formulas. And like he didn't want to just like take formulas on faith that they worked. He didn't feel like he really knew it unless he could derive these formulas from first principles on his own. So that's somewhat of the motivation behind building this spreadsheet. We're gonna really understand spreadsheets because we're gonna create one. So what do we need for this spreadsheet to work? For that calculate method to work, we're gonna think real hard, but we're gonna break it down a little bit. And there's two things we really need. The first is formula evaluation. Our spreadsheet needs to understand what a formula is and how to evaluate it. Like, how do you tell a computer program to evaluate 1 plus 2 and return 3 out of that? It seems simple when you're talking about it, and you've probably used compilers that do this all the time for you. Maybe you've taken a compilers class in college, and you have an idea how they work, but if you haven't, it can seem like a black box. So we're going to go through and kind of like open up that box and peek in a little bit. The second thing that we need for our spreadsheet to work is order of execution. So this dependency between cells, we have to execute them, we have to evaluate the values in each cell in the right order to get to the answer. If we can do these two things, then I think we can get our test passing, we can get to a point where we can call it a success. So formula evaluation, again, it's something like this. You type in a formula into a cell, 1 plus 2 times 3 plus 4, and you should get, the spreadsheet should be able to evaluate that to 11. You can also reference other cells in these formulas. So this one in A5 is referencing other cells to get its answer, 11 again in this case. And then order of execution, I wrote little notes in the column B here of what the formulas are for those cells. So if you looked at this, you'd be able to tell pretty easily the order that you had to evaluate these. You can figure out A1 because it's a literal, but if you want to know A2, you're going to have to figure out what A1 is first. And if you want to know A3, you're going to have to know what A2 is first. If you want to know A4, you're going to have to do A3 first. So we know, just because we can like hold it in our heads, that we will operate top down on this list. But there's more complicated spreadsheets. This is an example of like complicated dependencies. If you Google for like complicated spreadsheet dependencies, you'll end up on this Art of the Spreadsheet website where you can see cool things like this. But this is more like, this is tricky. I can't like tell the order of evaluation on this off the top of my head. And more importantly, we need to tell the computer how to do it, right? Okay, so let's start with these formulas. We want to create like a function. We'll call it evaluate. And this evaluate function, you should be able to give it a string. This is a string of some values. That's an expression. An expression is some math. And running this evaluate function on a string expression should give us the answer to it. So this deals with, we're going to build an interpreter. And if you've taken like I mentioned before, if you've taken a compilers class, these things are pretty well understood. There's been research for 50 years or more into this topic of how do you build a compiler, how do you build an interpreter, and we're going to approach it with starting with that kind of base of knowledge. So we're going to break it down into 3 pieces to build an interpreter. First, we're going to take that string, we're going to tokenize it. That means chopping it up into pieces. We're going to parse it, which means taking those tokens that we get out of the tokenized part and turning it into an abstract syntax tree. It's a big word for like a tree structure that has the values of our program in the right places. And then we're going to evaluate that tree. So this is what tokenize looks like. We're going to work through this particular formula because it's got order of operations in it, and it's fairly simple. So 1 plus 20 times 3, we can figure that out. The answer is 61, right? Because you 20 times 3 first, and then add 1 to it. It'd be wrong if you did 1 plus 20 to get 21 times 3, and that's, what, like 63 or something? So first step of that, we're going to tokenize it. We're going to get like some tokens out of here. You notice 20 is a token, and 2 and 0 aren't separate tokens in this case. Times is a token, and 3 is a token. So we can think of this token as like an array of token objects. Our parse method is going to, or our parser is going to take these tokens as input, and it's going to do some operations on them, and that we'll dive into in a little bit, to get us this abstract syntax tree that looks like this, or you call it an AST for short. If you've never seen one of these before, it may not look super intuitive what it is, but you'll see all of our tokens have ended up in this abstract syntax tree. The 1 has ended up over here. The plus got put up at the very top. Times is down below on the other side of it. And 20 and the 3 are down at the bottom of our AST. Once we have this AST structured in this way, then it's pretty straightforward to go ahead and execute it to get the value out of it. What we'll need to do is walk this tree. So we're going to start at the very top of it. And the first thing we're going to do when we get to the top of this is since it's a plus, we're going to say, all right, let's add some stuff together. And as we continue to walk down this tree, we get to the node below it, or a leaf. All right, we're going to add 1 and something else. And then it's a little bit of a problem. We can't just add 1 and a times, so we got to go deep into this. We got to walk down that tree and evaluate what this times expression is going to come out to be. So now we know, okay, well, we need to multiply now. So we can do that. We can multiply 20 and 3, so that makes 60. And then we've walked the tree at this point. We're kind of going to come back up out of it. And that times evaluates to a 60. And then now we can go back to adding at this point. And we know what to add. We're going to add 1 and 60, and we're going to get 61 out of it. So the algorithm to walk this tree, it's called depth first search. So we're diving down deep into it, and then we're surfacing everything back up. We're going to walk it to execute it. Okay, so let's dive a little bit deeper into the tokenized part. These 3 parts of our interpreter are going to be tokenize, parse, evaluate. So tokenization gets some code for this to tokenize this. Again, we're going to start with a test here. So hopefully that's big enough. I hope you guys can read it. If not, scoot up a little bit. But our tokenize in this test, you can see we're writing that it should tokenize A1 plus 20 times 3. So we call it tokenize on it, and then we're going to expect to get a bunch of token objects out of it. And these tokens, each token is going to have a different token type with it. We have a few different token types here. A1, we're going to call that a name, because it's the name of another cell. And then the plus is going to be a token type. And then we have a couple numbers in there, and the times is another token type. And then at the end, we just have an EOF, or an end of file token type. This is just indicates that we're done with our. Through implementing our tokenize function, we're just going to return an empty array to start with, and we can see that our test fails because we're not returning the right tokens. So what we really need to do is like loop through all these tokens, actually loop through all these characters in the input string, and then as we're chomping these characters off, we're gonna build tokens and spit them out the back. So at the beginning, we're gonna chomp off one character, spit it out. Then we might run into some white space that we want to ignore. we're just going to step right through that. And then when we get to like something like the 20, we're going to chomp off the couple numbers out of that, put it into one token, and spit it out. So this loop, all it is doing is it's looking at our input, which is that string, and keep in your head A1 plus 20 times 3 is what we're kind of like thinking about. Current is going to be the index, our current index as we're looping through it, and we're just going to get a character from that particular index in our string, and we're going to look at it to determine how we should build these tokens, right? So I mentioned we want to get rid of white space. We don't really care if there's a space between these, or if there's like space at the beginning, or two spaces between these plus and the number tokens. So this is just a little regular expression that tests, is this current character white space? If it's white space, we're just going to increment to the next character and then continue, like goes back up to the top of this while loop to continue iteration through the loop. So this little block of code just ignores white space from our input tokens. And if we run our tests again, we'll see that we get, it's just running, we get an infinite loop here. Because we just keep looping through these tokens and not incrementing. So we never like get far enough through this, unless we have all white space, right? So let's go ahead and we'll add another token type here. We're gonna look at that character and see if it's a plus. And if it's a plus, we're going to create a new token, and then we're going to push it onto our tokens array. And then we're going to increment our current spot in this string. So now we should be able to understand pluses, and if we write a test that just has a plus in it, we get a token out of it, success, right? We can also add this thing at the bottom, throw new type error. This will prevent our program from like getting in that infinite loop if it doesn't understand what a particular token is. So now if we have a new test here that has both a times and a plus in it, we'll see that it's broken again because our tokenizer doesn't understand what times is. So we do this, we'll add this one the same way that we added the plus, right? We just add another section down below that plus, that's the times. If we run into this asterisk character, we're going to create a new token, put it on our array of tokens, and then continue the next loop of this, this iteration. And we'll see that simple times and plus actually gets tokenized. So let's revisit some more complicated one where we actually have numbers in it. Our test is going to fail because we don't understand, our tokenizer doesn't know how to tokenize numbers yet. These are going to be a little bit more tricky. I've omitted the previous tests that we put, or the previous tokenizer rules that we put in here. But I'm not going to walk through this code, but the idea is if you run into a number, then we know we want to start building a number token. But we don't know what the next one could be another number, right? In the case of 20, it's a 2 followed by a 0. So we dive into this little while loop, and as long as the next number keeps, as long as the next character keeps being a number, we're going to build up this this token with a number and then spit it out. So we don't spit out 2 as one token, 0 as the next token. We build up 20 as a token and then spit it out. Now our expression, our basic expression, gets turned into tokens, but we're not really doing much with it yet. We've got tokens, which is great. This is A1 times 20 plus 3. So now we have names in here that we want to parse. And again, I'm not going to walk into how that works, but it's very similar to the numbers where you're checking if it's alphanumeric and building up a token. Okay, so we've got a good idea about how this tokenizer works. Now we want to build a parser. And I think this is the most interesting part about this process of like how do you build an interpreter in general. The parsing, turning these tokens into this tree is the trickiest part to get your head around. It's also kind of the neatest algorithm. The algorithm we're going to use is called a Prat Parser. So this guy's name is Von Pratt, and he published a paper a while ago. It was in 1979, or sorry, in 1973. He published this idea of a Prat Parser. So there had been a lot of research already on how to build these parsers. There's something called a recursive descent parser, where you look at tokens, and if you get to a token that is like a call a function, you kind of recurse into the arguments of that. So you parse the function name, and then this function is going to have arguments. Each of those arguments could also be a function in itself. So you recursively call down into these arguments. It's called recursive descent. A Prat parser is a neat little twist on that recursive descent algorithm. The thing that it does really well is it handles this order of operations. So if you remember PEMDAS from high school, please excuse my dear Aunt Sally is how everybody remembers it, but it's parentheses, exponents, multiplication, division, addition, subtraction. Another name for the Prat parser is the top-down operator precedence parser. So it's named that because each operator has a precedence associated with it. So I'm going to walk through a little bit of terminology, and these things, they'll probably seem a bit abstract at the beginning, like why are we talking about these? But these are like a few simple ideas, and if we keep this in mind, it'll help us understand this Prat parser algorithm. So when you're dealing with a Prat parser, there's basically two types of tokens. You want to think about your token as being either a prefix token or an infix token. And so what's meant by an infix token is something that's in between two other tokens and operates on two other tokens. So this plus operator, it operates on the 1 in front of it and the 20 after it. So it's an operator that has two operands, and it's between them, the way that we write it. So we call this an infix token. The ones outside of it, we're going to call prefix tokens. And this is just because if it's not an infix, as far as a Prat parser is concerned, it's a prefix. So it may be a little bit different than what you expect as a prefix, but just to keep in mind, these are infixes. Anything else is called a prefix. This is another example here. So we'd have -5 plus 3. In this case, we think about the negative symbol at the beginning being a prefix, because it's a prefix for the 5 actually. The 5 is a prefix just for the fact that it's not an infix. And then we have an infix operator, or what we're calling an infix token, and a prefix on the other side of it. The other thing that Prat parser is concerned with is precedence. So every token is going to have a precedence assigned with it. This is also called binding power in some terminology. And something with a higher precedence, we're going to give a number value to these. So like plus is going to be 1. It's going to be fairly low precedence. If it has a higher precedence, it means we want to do it first. So times should have a little bit higher precedence than 1. We're going to give that 2 is going to be our times. And then all these prefix tokens, they're going to be our highest precedence of 3, which kind of makes sense. You have to know that you have a 20 before you know you can multiply it to something else, right? So far we've got prefix and infix and precedence, and then at this point we're ready to start building our parser. So I want to start with building up a little bit of machinery for our parser to work, and this is just kind of like humdrum machinery that's pretty easy to understand and implement, but it lets us work with these tokens. So our parser should walk through these tokens. We're gonna consume them, and we're gonna be able to do a few things with this stream of tokens coming in. This is a test, and it probably looks a little bit complicated, but we're going to create our cellular parser. Remember, this is the thing that we're calling our spreadsheet is cellular. And then we're going to parse the expression to get an abstract syntax tree or an AST out of it. And then we just write up this expected AST. So you can see it starts with an operator expression at the very top, and that built up of three things: a number expression, the plus operator itself, and then below it on the right, we've got another operator, that's the times operator, that's multiplying 20 times 3. So it's like a nested structure, a hierarchy. This is how we represent our AST in code. So yes, we're going to call our spreadsheet engine cellular. So this is what our parser is going to look like. This is our base parser. We're just building up some machinery. So when you new up a parser, it's going to take an expression string, and it's going to keep track of that. It's going to use a tokenizer to tokenize that expression string and keep track of that in a tokens property. And then we're going to have an index where we can keep track of where we are in these tokens as we move through them. This consume method, the idea with the consume method is that our parser is keeping track of the state where we're at inside of this token stream, and consume is going to basically chomp off of a token and spit it out. It's going to return you a token, and it's going to advance our index to the next one. That's the only thing that this consume method is going to do. Look ahead method, this is going to it's going to kind of peek ahead, and you're on a current token, but this is if you want to know what the next one is to do something else, you can look ahead to see what the next one is. So you give look ahead 1, and it's going to return the next token in our array of tokens. So again, I apologize if that's too small, but we're just dealing with that parser. We're omitting a little bit of code so we can fit more up on the screen here. We're going to introduce a new thing here. This is a map. It's the token type to precedence map. So remember, each of our tokens has a precedence, 1 for plus, 2 for times, and 3 for our prefixes. So this is just a way for us to keep track of if we have this token, what's the precedent for it? We just look it up in the map. And then we're going to add this other method called peak precedence. So this is looking ahead to the next token and returning what the precedence of that token is. So all of this so far, it's a bunch of little pieces, but they're easy to understand. And then we're going to see how these kind of come together in just a minute. So we're peak precedence gets us to the precedence of the next token. Again, this is what the precedence looks like for our tokens. 3s for the 1, 20, and 3 numbers, and then 1 and 2 for the times. We're going to add a couple more maps here, and this is where some of the Prat Parser machinery comes in. Each of those infix tokens and each of those prefix tokens, they're going to have their own little parser that goes with them. So if you have a prefix token, there's going to be an associated function that knows how to parse that particular token type and return an expression. So something like a plus should return a plus, an add expression. Something like a times should return a multiply expression. And something like a number is going to be a prefix there's a prefix parser that will look at that number and return the actual value as a number type instead of just a string. So to support this notion of having these little parsers that are associated with each token, we're going to add a map of prefix parse functions. This is mapping a token type to a function that knows how to parse it. We're going to do the same thing for the infix parse functions. We're going to have a token type that maps to a function that knows how to parse it. All right, so for example, here's some prefix parse functions. This is a parse the name and a parse a number. The name parse function just returns a new name and it looks at the value of the token. These are super simple, right? Parse a number, we basically cast this string that's representing a number into an actual number, and then we return that as a number expression that has a property on it of a number. And then an example of our parse binary operator. This is an infix parse function, and we can use this one for either plus or times. A binary operator is just something that has 2 operands with it. This one's a little bit trickier because each of those operands could be not just a solid number, but it could be like a more in-depth expression. So this is where we dive into that recursive descent. You see in the middle of it, we call parse expression, where we pass in the precedence of this number. And then what these expressions look like, they're just simple classes that hold the values for numbers or names, operators. Our parser is looking like this. We're going to add a parse expression function to it, and this is where the kind of the magic of the Prat Parser comes in. This parse expression is going to look at a left token. It's going to parse that left token. It's going to look up the correct parser function in our map for it, and then it's going to, in the case of 1 here, it grabs like a number parse function, and then it actually turns that into an expression. So this is where we build that node in our tree. We get an actual expression from our token. This is the brilliant part of the Prat Parser, and I encourage you to like look at the code and like maybe debug it and walk through this a little bit. This is the thing that does the recursive descent in the right way to handle our operator precedence. It's looking at the precedence that's passed into our parse expression, and as long as that's less than the precedence of the next token ahead, the peak in the precedence, then we're gonna basically grab the infix parser and parse it. In the case of our binary expression, I'm gonna just add that up to the top here. In the case of our binary operator parser, this is where we'll get back like the binary operator parser, and then we dive into it. Now, I know it's hard to get your head around it right now, and we don't have time to do it, but the thing to keep in mind, like, think about the precedence at the very beginning is going to be 0. Each of these has precedence. This nice little Prat Parser algorithm will go through these, and it'll build this tree, and the thing that it returns at the end is this plus expression up at the top. That's the thing that gets returned out of our Prat Parser. So now we have this cool tree that we can go ahead and execute. So we're running a little bit short on time. We're going to skip through a few of these really quickly. But now that we basically built the machinery for our Prat Parser, this is how we introduce like the things or what we call the grammar for our parser to understand. So our parser should understand numbers, and it should understand plus and times. We introduce a couple of prefix parse functions here that we can use one of those to parse a number. We can use one of those to parse a name. We introduce a couple infix parse functions. We can use one of those to parse plus, one of those to parse times, and then we set the precedence here. So we're setting 1, 2, 3 in order from plus times to name, and you can see that this cellular parser is a class that extends our parser. So we built all the machinery, we kind of tucked that away into the parser, and then to define the actual grammar of what we're building, we can do it all very, very clearly in here. So this is kind of the benefit of using this, not just a Prat Parser, but kind of like what's known for parsing in general. We get to break it up into clean pieces that we can understand and we can reason about. So surprisingly, and amazingly, that's all we need to get our Prat Parser to work. It's actually not a lot of code, but since it's recursive through a couple different functions, it's a little bit to wrap your head around. So take some time to look at the code in depth. So this is our test again, and we see that it's passing. Okay, just like 5 minutes left. So I'm going to blow through this order of execution, and then we'll have the stuff we need. So if we look at a table, we have here an example of a small table, and you can see that some cells reference other cells like this. You could represent something like this as an array of arrays in memory, But what works a little bit better for us is just to keep like a map of nodes, which we're already keeping this map of cells, right? And we think about these as a graph of dependencies. So every time we have a reference, that's referencing another cell. And we think about these cells and the other cells they reference as a graph. We're calling this this thing is called a DAG, a DAG, or a directed acyclic graph, just meaning there's no cycles in this, and you can't have like a cell that references a cell that references that first cell. You'd have a loop. And there's an algorithm called a topological sort that we can do on this graph. And the idea with that is, with a topological sort, is you just iterate through all your cells, so you're not even aware of what order it is. You're just going to iterate through your cells, and you follow this rule. When you get to a cell, if it has any dependencies, if it has any references, then you look at those, and you evaluate those. If the cell has already been visited, you don't visit it. And when you're done visiting a cell, you put it at the beginning of this list. So we're going to walk through that real quick here. A1 is just our first one in the list. We add it to our sorted list because it doesn't have any references in it. Next up is A2, because we're just walking through these. Again, we just add that to the list. A3, it references A1 and A2. We would go actually walk those, but they've already been visited, so we don't need to. At this point, we visited all the references for it and we're done. We just put A3 on our list here. We keep walking, we get to the top of the second column, B1, that's A3, and so here we would go walk and get to A3, but since it's already visited, we're kind of done with B1, we add that to the list. B2 is the next up in our iteration, and in this case, it actually does reference a cell that hasn't been visited yet, so we go and visit that B3. It doesn't have any references, so we're done, we add that to the list. And then we're done walking B2's references, and so we add that to the list. So if you look at our sorted thing, this is actually sorted in a way that we can execute. We execute it in this order, and it just works. All the dependencies are like figured out for us. So I think that's really cool. This is called a topological sort, and a topological sort can be performed on a graph as long as it's a directed acyclic graph. You can do this topological sort using this like simple algorithm of walking the tree depth first and putting these cells on the list as you visit them. So here's some code that'll actually do that. We don't have time to go into that, but it's in the project. This project, I called it cellular, just because Spreadsheet has cells and like. It made a cool like logo, like plant cells, right? So if you want to check it out, go to, you can find it on NPM as cellular.js, and you can actually go run this in your browser. A couple of books that I really recommend if these compilers interest you. This first one is called Interpreter Book, and it's how to build an interpreter with Go. Even if you're not familiar with the Go programming language, this book is like super accessible. It's an easy way to like get into how like an interpreter works. And then this other one is kind of like this big fat textbook of algorithms, and it's taught in schools and stuff, but it's really a good book if you want to understand some algorithms. They talk about algorithms being should be treated as a technology, like maybe we have technology in our cars or our computers. Algorithms are another form of technology that's purely knowledge. Cellular.js is on my GitHub account. If you have any questions or comments, or you want to start adding some functions for cellular, just shoot me an email at lance@submittable.com. Thanks everybody for attending.